Welcome to the 52nd lecture of surface engineering. In the previous lecture, we discussed application of electron beam primarily for welding purposes, and we realized that electron beam offers one of the biggest advantage possible by way of deep penetration welding, which is not possible with other kinds of be it directed energy or conventional tools. But then EB is not necessarily only meant for welding. EB also has a large number of applications, particularly a very specialized application for surface engineering, and that's what we need to discuss now today. So let's go straight away into the configuration. You have seen this view graph in the previous lecture. So essentially we have, these are the constructional features. We have an electron beam gun. We have a power supply which applies very high negative potential difference to give kinetic energy to the electrons. We need a control system. We need a sample manipulation stage, and of course very high vacuum chamber. So this is the overall setup, and this is the high voltage cable and the tungsten cathode which emits electrons, the bias cup which actually deflects and makes the beam, the primary anode which has certain central hole, the electron beam. This is the electron beam, and this is how we actually focus. And for focusing, as I mentioned, please recall that we need both electromagnetic lenses for focusing as well as deflection or deflecting, so that we actually are able to irradiate exactly the desired spot and not elsewhere. Maybe this is the desired spot, but if we want to move from this spot to this, then we need to move the stage along this direction or the other direction. So there could be a relative motion between the beam and the workpiece. And this is where we get the, either call it a weld piece or maybe the surface melted zone. So this is the overall setup. We must quickly recall that we require very high vacuum, and since there is no extraneous material present in the form of shielding gas or flux or anything, so it's a very clean process, and we need certain stage manipulation. If we want welding, of course, then we don't need a filler, but if we want surface modification, surface cladding or surface alloying and so on, then we actually can have a pre-deposited layer or sort of already an available coating, and then we melt the coating along with part of the substrate and create an alloyed zone. But we can also feed in material inside the chamber. So we'll come to that in a minute. So this is the overall setup. This again is repeated from the previous lecture just to bring home the point that the same configuration, and we require the similar mechanisms for focusing, for deflection. Also we need a viewing port, and we need to maintain very high vacuum before we start the electron flow. And eventually once the irradiation occurs, then this is how the surface of the solid undergoes melting process. But this also is important to recall that when the incoming electron beam interacts with the solid, it actually creates a heat affected zone or hot zone below, and in the process, because of this high stream of particles charged particles carrying very high kinetic energy, when they're incident onto the surface and when they interact with the solid, they can emit secondary electrons. They can certainly create heat radiation out of the surface. They can also create not only secondary electrons but also backscattered electrons. It can also emit certain amount of X-rays, because you're rapidly decelerating the incoming stream of electrons, and that rapid deceleration can actually lead to emission of X-ray. So you need a good protection around. But the most important thing is, in no time, the incident beam will interact with the solid matter, raise the electrons to higher energy state, and allow the electrons to come back to the ground state. And in the process, it will allow the heat to be absorbed by the solid, and this will be converted into lattice heat. And then heat flows. Heat flows vertically downwards and also laterally to some extent, depending on the relative size of the diameter of the beam with respect to the substrate thickness. So this is the processing zone, the so-called processing room. You also need a compound desk on which the substrate, which may be a small light one or maybe a very large thick one, and you also need to be clamped well so that it doesn't deflect during the processing period. Then you need so this is your workpiece, which is placed here. You need the electron gun here. So this is the electron gun, which actually emits electrons. You need a cathode. So this is the cathode through which the electrons are emitted, from which the electrons are emitted, and towards the anode. So from this side, you actually will have it, the emission will take place towards the cathodes, or the electrons will flow towards the cathode. Then through this opening, central opening, the electrons will flow, but you also need some kind of a covering to cut out the stray radiations, and then this. The configuration actually, this entire, this is the electron gun part. So in the electron gun part, this you have the filament, the cathode, the anode, and this whole thing together is called the Wenelt electrode. Then you have the focusing lens here, you have the deflection lens here, and so you actually can, at the moment, let's say the point of contact is here, irradiation is here, but you can also deflect to this point or this point. So this deflection or rastering is possible by manipulating through this deflection coil or the reel. Then you need to evacuate, maintain very high vacuum. So this is how you maintain very high vacuum, and this is how the beam interacts and then converts the kinetic energy of the electrons into the lattice heat of the solid substrate. So we can, for example, build components like this vertically. We can build a component like this, or we can irradiate only this part and not elsewhere. Similarly, we can irradiate or heat up only this part, or build a material at this sharp part of the shear blade and not the rest of it. So we can create additional layer, and for example, the way they have written 1 and 2, likewise you can build certain structures. You can even irradiate only these portions, the conical portions, the sharp tip of the conical portions, leaving the base regions completely unaffected. So material wise, all kinds of steel, maybe low carbon, plain carbon steel, or medium or high alloy steels, all these various series, then periodic matrix cast irons, various tool steels, work hardenable, oil hardenable, or hot working tool steels, and so on. So various types of ferrous materials are ideal to be treated, but you can also do for titanium alloys, magnesium alloys, or any other reactive material. Zirc alloy, for example, is a standard material for all nuclear power reactors, and electron beam facility is ideally suited for such highly reactive materials like zirc alloy, which is zirconium containing alloy. Similarly, niobium alloys, or which requires very high melting temperature, or even dissimilar cases when you would like to create a clad on zirc alloy with another composition. So electron beam would be ideal for that. So the term hardening here does not necessarily mean only phase transition, what we generally are used to, of austenite converted to martensite. This means also creation of hardened layer onto the surface, including by way of cladding. So these are the processes. So obviously, if you want to harden the entire surface or with create a coat, then you start with a certain layer, and then you go layer by layer and then make it wider. And when you have done the whole surface, then you will definitely see certain level of overlap. So if this is a particular layer, the next layer will not begin exactly at this surface, at this interface, will begin somewhat here. So one layer created like this, the next layer will actually start somewhat in between. So there will be a certain overlap here. And that's what you see, but very nice geometric and precise bead sizes. So typically across the bead, you'll see that the hardness wise actually there could be variations, and that's purely because of the treatment or the composition that you actually are treating. The various geometries are possible. You actually can make stripes or make dots or circular dots, or you can create oscillation of the beams and create certain complicated shapes. So the point is that on a flat surface, for whatever reasons, if you would like to treat these kind of stripes or create these kind of stripes and leave the portion in between unaffected, or you create certain patterns like this, which are maybe circular or some geometric shapes, but leave the rest of the surface unaffected, or on the surface you actually would like to create such special shapes or contours, that's also quite possible with electron beam. So anything like irregular path or a circular path or certain area coverage and so on. So all these are possible. So essentially we have to ensure that if this is the substrate and this is the beam, then we need either of these two to move to create surface integration. So if this is the surface we are talking about, so we need one beam to cover like that, another like that, and likewise this is how we can cover the entire surface. And when we do that, then as I already mentioned, that there will be a certain overlap. The next beam will not start where we ended, but will actually start somewhat already covered area, so that there is uniformity in the microstructure across. One of the biggest application in terms of surface engineering using electron beam is related to cladding. And this means that, for example, the worn parts of a very expensive tool or shaping tools, maybe cutting tool, or maybe a nozzle, or maybe even a gear or something, if it doesn't make sense to throw away or replace with a new one because the component is a very expensive one, then one can actually try and clad the same alloy composition or a different alloy composition by using electron beam as a source of heating and melting. So either you have pre-placed powder, which with certain binder you actually can create. So if this is a component surface on the cross section, you can create a top layer and then use a electron beam to raster over the surface, so that not only the top layer melts, but the molten layer also dissolves a part of the underlying substrate, so that you form a nice bond here, and in the process you actually develop a much harder layer on top. It's not only about hardening the layer, it's about also restoration of the, or basically if a particular component has developed some crack or some dent like this here, you actually can refurbish or reclaim this by way of putting material here, and this precise filling up of the crack or the gap is possible by way of either feeding through a filler wire or fill the gap with certain powder and then use electron beam to cover this area. And when it melts, if the composition is the same as the substrate, then these interfaces are practically invisible. They actually integrate very well with the component. So cladding is a very important application. In fact, on components which is, for example, margin steel or high alloy tool steels, or even zircon alloy or titanium alloys and so on. So this kind of possibility is certainly very useful. So we can feed by into the molten pool by way of powder. It can be, instead of powder, it can be wire, it can be a tape, it can be other forms in whichever way you actually can create. So the molten layer will solidify and create a good metallurgical bond, and this is done in vacuum and with very high precision. So obviously there is no, in most of the cases there will be very little requirement of subsequent processing or machining and so on. The liquid metal pool which actually solidifies within this gap, say for example if this was the gap and you have filled it up with the powder and then you're melting, or you're feeding filler metal and just allowing the liquid to flow in and cover. In such situations, when the melt pool solidifies, you actually can't make out any difference after this, and there is no need of any surface machining or any other post treatment requirement. There is no further annealing or anything required, because this volume is very small, is the same composition as here, and there is very good wetting here inside the cavity. In the process, you also see a lot of grain refinement and creation of certain residual stresses. Now, this is something which one needs to be worried about, because in any fusion process, we all are aware that generally the residual stress is tensile in nature. So, on the surface, be it welding or surface engineering, if you generate residual compressive stress, then this is not so good news, because if you form a crack by some means, there will be an easy chance of opening of the crack and failure and leading to failure. So, one needs to find out as to how you can reduce the relative degree of residual tensile stress on the surface, or if possible bring in residual compressive stress on the surface by way of some special treatment. So, the thickness that you require will depend upon, of course, the parameters, the current and the energy or the potential difference that you are, also the relative position of the weld of the electron beam focus, but also the feed rate or the speed at which you feed material in at the melt pool will determine what would be the relative thickness of the clad or the refurbished layer. I mean, clad essentially would mean as if you are cladding the whole surface, then you call it cladding. But when you are repairing only a small part of a, let's say a particular shear blade, so this is the shear blade which actually got worn out. So you are treating only this part. So this is refurbishment, this is reclamation. Whereas if you want to put a hardened layer on throughout the surface, you call it a cladding process. So this is a typical microstructure done on a tool steel. The temperature that the metal sees will decrease from the surface to the core. And yesterday we did discuss about the way the ion beam interacts with metal, and there, if you recall, while discussing ion beam, we did say that the deposition profile is Gaussian and the peak is below the surface. The same deposition profile or the feature applies to electron beam as well. Though the penetration depth is, one can vary or is controllable, but what is not controllable is that the peak temperature is not at the surface but below the surface. And hence, because of this reason, EB is more suited to deep penetration welding than shallow welding, or for that matter surface engineering applications. But nevertheless, this peak is not too far below the surface. So if you are doing a cladding operation, then EB can be ideal. And it is also very ideal because if you are dealing with components which are very reactive, for example titanium or magnesium, which easily would always react with oxygen present and then create oxidation. So what all we discussed in this surface engineering application of electron beam? For reactive metals, for sophisticated or expensive components, we can use EB also not for joining alone, but also for surface engineering. And the biggest possible surface engineering application could be, for example, cladding or simply surface melting because melting and rapid solidification, because of the rapid heat extraction during the solidification process, allows a very small grain size or high nucleation rate, low growth rate. As a process, in the process, we actually end up getting very small, tiny little crystallites throughout the surface, and they don't grow much, so we get large grain refinement effect. The process parameters, just like welding, here also the beam current, the applied voltage between the anode and cathode, the degree of vacuum, the degree of overlap, the relative position of the focus with respect to the substrate surface. All these are very standard process parameters. Since the whole process is done at very high vacuum, it's quite possible that the cooling rate that we effectively get in case of welding or surface engineering using electron beam is not as high as one can get in, for example, laser processing. So that's a limitation. But it's also at the same time should be argued that laser or many other processes actually are done in air. So if you are dealing with zircaloy or zirconium or titanium, which is very high magnesium, very highly reactive ones, then EB is better suited than other processes. But EB is not an ideal tool, not necessarily an ideal tool for surface engineering. Why this is still used for surface engineering? Because if you want to clad or harden or deposit or simply surface melt a very sophisticated and a very reactive metallic component, then the high vacuum that you have in case of electron beam is very, very helpful. And of course, another very big advantage is that it probably can melt anything. If you apply good combination of time and power density, you actually can melt almost all possible solids, unless they decompose even before melting, like diamond. You would rather use sophisticated, expensive, complex shape and other major specialized requirements by EB assisted welding or surface engineering, and not necessarily do things which are done routinely outside, can be done routinely outside using even just an arc torch or arc melting unit or TIG or MIG unit and so on. Just because this unit itself carries a large capital cost. No, you have to have the whole chamber kept under very high vacuum. You also require the electron beam. You need a gun, and the gun should be able to provide you stable substrate, stable electron beam to hit the substrate surface and melt or do other things. So then you have to need a protectant chamber so that the emitted electrons, secondary backscattered or X-rays don't actually go and create problems for the operator or anybody outside in the room, same room. So after this, we'll move into the third possible direct energy beam called laser, and you'll realize that laser actually could be a much more versatile tool for surface engineering than electron beam. But we must realize that there are niche applications where you would rather use electron beam and not laser, depending on the scopes of oxidation or reaction with atmospheric air or other gases present, or maybe some other specific reasons. But if you are dealing with components of sophisticated components which are expensive, the material is very expensive and at the same time very reactive, and you are not willing to take any chance, then of course electron beam facility will be most handy either for welding or for surface engineering. So thank you very much.